second last talk in this session, MixMatch, flow matching for Mixnet traffic.
Thank you. Hi, I'm Leonard. I'll be presenting MixMatch flow matching for Mixnet traffic, and this is work with Mark, Enrique, and Claudia. And this paper investigates the question how well a state-of-the-art Mixnet, in this case we analyze NIM, prevents passive gateway adversaries from linking communicating endpoints using only the packet metadata. So this comes down to the timestamps and the size of the packets that they send. A little bit of background on NIM. What is NIM for us here? NIM aims to be a general-purpose anonymous packet routing layer for a large share of applications that can communicate over the internet. In terms of its mixnet properties, it's a continuous time mixnet. That means it treats each packet independently. It doesn't assemble them into batches. And it also enforces pretty strict, or it stipulates pretty strict traffic shaping properties for endpoints that are connected to it. Specifically, endpoints will shape their traffic to follow a Poisson process that they send through NIM. Relevant for our work is that we use NIM as the stand-in for a state-of-the-art mixnet. Because its code is available, it is a deployed system and it's under active development. To visualize this just a little bit, you can see here many of the relevant parts of NIM's infrastructure, specifically on the left-hand side, the users and the service providers, which we just call endpoints because their role doesn't matter to us. On the right-hand side, you see the Mixnet, consisting of the mix nodes, that is responsible for anonymizing the packets, and in between, there is an interface layers of nodes called gateways, and they keep some state for the endpoints connected through NIM. They will also, I understand that eventually they will be billing them and so on. And these nodes are really relevant for us because we assume that the adversary is running some of them and conducting the flow matching attack at this point, right? So the adversary is internal, running some of the gateways and matching flows at this point. How can the adversary do this? In the paper, we discuss two traffic features that can be exploited to conduct flow matching. The first of them is shape, we call it shape. And it's really what you would expect of it. It's the intuitive notion of like seeing how traffic progresses over time and then matching based on similarity of like how similar they look. So I hope you agree with me that it makes sense to guess that egress 2 is the egress flow for ingress and not egress 1, right? Because of how similar their shape looks. Indeed, there's previous work in the context of the anonymity network Tor that exploits this traffic feature shape, specifically the two systems Deep Coffee from 2022 and Deep Core from 2018. And they are also really relevant for us because they were the foundational papers in the space to use deep learning methods for the traffic correlation setting. We adapt Deep Coffee into our deep learning classifier that we call Shape, very original, to test how well the best attack against Tor works in the much more difficult context of mixnets, specifically again NIM mixnet, right? However, as I already mentioned, NIM enforces pretty strong traffic shaping behavior of endpoints. Remember, they will shape their traffic to follow a Poisson process, which means that shape features are strong, heavily diminished, right, in terms of like how much you can exploit them for flow matching. So the adversary will might need a secondary one or a different one, and this is drift that we also discussed in the paper. So when endpoints send their packets following a Poisson process, this means that they will, on average, send constant bandwidth through NIM. And if you think of like two NIM endpoints that are connected through NIM, you can think of this visually as like a pipe of a known constant diameter through which they will send their packets, right? Like going in and coming out. And if that is the case, we can expect that their difference in timestamps of the egress timestamp and the ingress timestamp at the same position in the sequences, that this follows a known and low variance distribution. And we can visualize this so you can see the difference quite clearly. The delay distribution for matched flow pairs is shown in blue, and it differs like significantly from the delay distribution of unmatched flow pairs in orange. And we can use this to build a test that says, okay, does a test flow pair like correspond to the expectation? In this case, we classify it as matched. If it doesn't, it's unmatched. And the naming comes from the delay distribution drifting away from the expectation. That's the idea there, right? We use this to build two classifiers. The first of them is called statistical, and it models this drift distribution explicitly, and then computes likelihood scores for the candidate pairs. And the second classifier is called drift. It is a deep learning based classifier that learns the underlying distribution of the drift from the large data sets instead of modeling it explicitly, right, using a convolutional neural network. We have to make two important assumptions for the setting of flow matching. The first of them is that the sets of endpoints under consideration are expected to communicate exclusively among themselves. Right? That means these sets can be of any size. They can be of like size 2, size 5, size 10 or more. However, you cannot have any out-of-set packets. So any kind of packet that is part of the evaluation needs to be within the set of endpoints under consideration. We propose a technique that we call flow merging that enables us to transform the flows that we collect for our evaluation to be much more usable with our classifiers. So you can see it on the left-hand side. This is the representation of the independent flows for 3 endpoints connected to NIM, and then you can transform these 3 independent flows into a joint merged representation that works nicely with our classifiers and also gives us the ability to take care of NIM's loop cover traffic because NIM sends a type of cover traffic that loops back to the sender. The second big assumption is that any packet sent is assumed to be eventually received within the set. So for a large part of our data sets, we assume that there is no packet loss, and I can go into a little bit of detail later. So we evaluate our 3 classifiers, shape, statistical, and drift, using 6 data sets, out of which I will only discuss 2. The first of them is called baseline. It is a default NIM configuration, so we don't mess with packet timings or sending behavior in a lab-like setup, in an isolated setup, where there is no propagation delay and no packet loss. And we do this so that we can focus on the core contribution of the Mixnet to the anonymity or to the protection against the adversary in this case. There's 4 more data sets that we collect, but I will not go into detail here. You can find the results in the paper. And then the second relevant data set is called live NIM. It is again default NIM, so unmodified sending and delaying behavior. However, this time it's not in the lab-like, no network effects setup, but on the live deployed NIM network. So that includes propagation delay and packet loss and other network artifacts. Let's look at some results. Our result plots are receiver operating characteristic curve plots. So that means we show the true positive rate versus the false positive rate. Mind that the false positive rate is a logarithmic scale. And we plot the performance of our classifiers here. And specifically, we always want to be at least better than the random classifier, which is shown in green. And the best classifier would be in the top left corner. That would be a perfect classifier. And what you can see here is that the more data that we feed our classifier, so this is the number of observations going up, the better the performance, the flow matching performance gets, until ultimately we reach almost perfect classification. However, noteworthy here is that even only feeding 100 network observations already yields relatively good performance. Specifically a true positive value, a true positive rate of 0.6 for the drift classifier, 0.47 for the statistical classifier, and a false positive rate of 10 to the power of -2, which is already quite good. We don't show the shape classifier here, as you might have noticed, because initial evaluations showed that it underperforms the other 2 classifiers significantly, so we focus on the 2 better performing classifiers for the majority of our plots. However, not for the next plot, which contrasts the dataset baseline and the dataset live NIM that I introduced earlier, right? So remember, this is both default NIM, but once without any network effects, once with network effects. And we can see that the shape classifier is, in both cases, is much worse than the 2 other drift-based classifiers. Right? However, maybe even more relevant here is that the introduction of real-world network effects has a significant impact on our classifiers, which reduces their classification performance. Which we attribute to these network effects kind of invalidating the flow matching assumptions that we make for our classifiers, right? What our classifiers are based on. Okay, so this impression gives away the primary idea for a countermeasure to a flow matching attack against Mixnets, which is to invalidate the exclusive communication group assumption, trying to introduce cover traffic that is not seen by the adversary, so that the adversary would have to increase and increase and increase the observed, the set of endpoints under consideration, if it is even visible to the adversary. This could be achieved through two means. You could send cover packets that are supposed to be dropped along the Mixnet path somewhere, like one mix is instructed to drop it. Or you could send cover packets that are addressed to as large number of random endpoints as possible, as well as receiving from as large number of endpoints as possible. With this, I'll go to 4 takeaways from this work. First of all, Mixnets are a powerful tool for network level privacy, but they were designed for single packets or short flows, not the long flows that we see from like any modern application workload that you send through the internet. The second takeaway is that under the assumptions that I presented, our attacks are fast and accurate, which shows that even a modern and like state-of-the-art Mixnet such as NIM is not immune to this de-anonymization threat. However, this setting of like long flows, or like let's say just regular flows nowadays, plus an adversary that is internal to the system sitting at both ends of the connection, right, at the gateway position, is very hard to protect against, and we need more research to work on this open problem. And the final point is that the difficulty of the classifiers with missing packets indicates that an avenue for a countermeasure to our attack, to this attack, specifically to break this endpoints closed set condition. With that, I thank you, and I'm ready for questions.
Hey, thank you very much. This is really cool work. So I really appreciated takeaway 1 because in the previous talks I was only thinking about single messages when we were talking about mixes. And I wasn't really sure how flows work in NIM. So is it like, do all the messages between two communicating parties go through the same series of mixes, or is it something else?
They don't go through the same series of mixes. Each packet takes its own path through the Mixnet, so each packet will use its own cryptographic key material and take its own path. They are only streams or whatever at the endpoints, right? So they go like, okay, it depends on how many gateways you connect to, but assuming that you connect to one gateway, this would see like all the packets in between that link, but then through the Mixnet, it's one path per packet.
Thank you.
Thanks for the talk. You mentioned that there are network effects that invalidate your classifiers. Did you look into that? Do you know exactly which effects those were? And could you say more about that?
So invalidate in the sense that they diminish the classification performance. They don't like break them entirely,
Yeah.
and we also think that there might be ways for how we can like be better in those cases, right? But the assumption is that any kind of network effect like packet loss, for example, of course invalidates this assumption that every packet will eventually be received that is sent within a set, right? Of course the packet loss invalidates this, which makes the classifiers based on drift struggle because they don't have a perfect ingress-egress packet index match anymore, right? So those are the network effects that we are talking about.
Do you have analysis in the paper on the performance in the face of those real-world conditions that you can't get around?
Yeah, so the data set live NIM captures these, right? So we
Cool.
show the performance in this setting. So yeah, some analysis of this is part of the paper.
Thank you.
Yeah, so on that note, this is Harry from NIM. Could you describe what was the baseline again?
Baseline was like default NIM, no changes to how packets are sent or delayed in an isolated setup, which means no propagation delays, no packet loss.
So was that the NIM software, or was that a simulator?
There was NIM software. Yeah.
Okay, so you're running NIM software
Yes.
on your own controlled environment.
Yes, indeed. It's a single host.
Yeah. No, I mean, that would make sense. So I mean, it's interesting. I mean, in live NIM was just whatever we were running at the time we did the attacks,
Well, it's
which I think was the unparameterized testnet with no adaptive cover
it's
traffic.
the live deployed mainnet that we hooked up our private data collection.
Yeah, I'm just going to note that we haven't added cover traffic or adaptive cover traffic to the mainnet, and we didn't parameterize the mainnet. So you're essentially running, like live NIM is whatever random parameters Anya Petrowska chose half a year ago whenever you did this work, right? So it would be interesting maybe to try, for example, longer mixing parameters, more cover traffic, adaptive cover traffic, which is what we're working on now with Carmela. I think would probably help. We also noticed that and I worked with Carmelo, which is we're doing a poster session on that. Actually, I mean, Tor is great. Performs in the real world actually a little bit like a Mixnet, just because there's fragmentation on the traffic level, right? That being said, it's very good work. I would suggest for future work of this type, running it on the actual parameterized network and not random test nets.
To clarify,
then,
we ran it on the main net.
Yeah, but if you run a network on like an imaginary environment, then it's like you get imaginary results. And then the second thing I would point out is that like your threat model is pretty strong. So I think it's a true threat model, but like it's not surprising. I think it would be the same with Tor, that if you control both the entry node and you assume that all the traffic is going to be one entry node, and you control the exit node, and you can assume all the traffic is going to that exit node. So both entry and exit adversarial, and you're running machine learner over long sets of traffic, like, of course the attack will work. So I don't think the result is, I mean, we didn't consider it very surprising, and it would be equally devastating to Tor or like any other system.
100%, like, no question, for sure. I think it's a realistic threat model in the sense that the adversary only needs to run some gateways, right? It's not assumed to run all gateways or even to be able to see all the traffic, not at all, right? It's only able to conduct these kind of attacks on the traffic that it is able to observe at its own gateways, which, you are able to run gateways on the main net, so it's possible for an adversary to get into that kind of position. But yes, of course it is, it comes with its own set of strong assumptions for sure.
Sounds like an interesting discussion to have over the break, but before then, we've got our final talk of the session, which is recorded section. So could someone cue that up, please?